Today we're going to take a look at page 239, 5.1, which is talking about the nth roots, radicals, and rational exponents. Nth roots is kind of just a fancy way of saying you don't know what the root is. They plug in the nth instead of saying the second, the third, the fourth, because it could really be any root. The 12th root, it just doesn't matter. So the nth root is just a way of saying you're taking a root, you just don't know if it's this, to what degree it's to. Let's go ahead and kick off with example 1 at the bottom. So there we go. Find all the real nth roots. When they say real, they're just emphasizing the idea of different types of numbers, right? Like integers, rational numbers, natural numbers, counting numbers. There's all those different, what do you call them? Groupings of numbers. Real numbers are just a fancy way of just saying a specific type of number. So a real number could just basically be any number. It doesn't matter what the number is. What are all the real cube roots? So that's when you're taking the third root of 125. So it's starting off with some vocab. The nth root of a number is of a number C. So they're just saying any constant, that's what C represents, is X. So you can take the nth root, which is the square root, so the second root, the third root, which is the cube root, the fourth root, the fifth root. Doesn't matter what root, they're just saying it's X. Such that X to the nth power equals C. So you can go back and forth between an example like, well, let me just go ahead and make something up. If I say like, the cubed root of X, I can rewrite that as X to the 1/3 power, okay? They go back and forth. Sometimes one, the way you write it like this might make more sense, but you can also write it like this. Just be aware that you can go back and forth between the two things. So I can write it like this, which is a traditional root. If you write it like this, that's the square root of X. If there's no what they call index number there, if there's no index, then it's automatically a 2. It's the square root, it's the second root. But they could have something like this, the 6th root of X. And then they could rewrite this as, since this is the square root, it would be 1/2. Since this is the 6th root, it would be 1/6, okay? An nth root can be denoted by a radical symbol with an index. So this is kind of like what we were talking about of n. N is the number, the root you're trying to take that to, and then n root c. So it could be written like that, or it could be written as c to the 1/n power. C is called the radicand. So whatever's underneath there, it could be a number, it could be a variable, it just depends on what you're given. But whatever's underneath that root is called the radicand. And then like they say here, n, whatever the degree of that root is, that's called the index of the root. So to represent the real cube root of 125, write x equals the cubed root of 125. Again, you could write that as x equals 125 to the 1/3 power. It's the same exact thing. Doesn't matter how you write it. Just know that you can go back and forth. So if they give you a problem like that, don't stress. It's just basically saying the same thing as x equals, I've got my root, 125 will be my radicand. And the way you break this up is it's exponent over index. So the number on top is the exponent of my radicand. So this is 125 to the 1st power. And then the number on bottom is the index, basically what I'm trying to take that root of. I'm trying to take the 3rd root of 125. So just keep that in mind, exponent over index. That's how that works. To represent the cube root of 125, we would write x equals the cube root of 125. To find the value of x such that x cubed is 125. This is kind of going into some kind of verbiage definition, but I kind of want to simplify it a little bit. So let's go ahead and write out what they have. X equals the cubed root of 125. So keep in mind at this point that if I say the cubed root of 125, well, the opposite of taking the cubed root of something is raising both things to the third power. Just like if I have something like this, x plus 2 equals 7, right? The way to solve this algebra equation is to just do the opposite. That's all you're doing. You're always doing the opposite to solve for x. So in this case, what's happening with x is I'm adding 2 to it. So the opposite of addition is subtraction. So I get x equals 5. Just like if I have something like this, 3x equals 9. What's happening to x is I'm multiplying it by 3. So the opposite of multiplication is division. So I need to divide both sides by 3 to get x by itself. Well, what's happening here is I'm taking the cubed root of 125. So essentially what I need to do is the opposite of the cube root is to cube it. So if on the right side, if I have the cubed root of 125 cubed, that's the same thing as 125 because the cubed root and the cube just kind of undo each other. They're opposites. And then on the left, I can write that as x cubed equals 125. So again, they're saying the exact same thing. X equals the cubed root of 125 and x cubed equals 125. It's the exact same equation. It's just a different way of looking at it, okay? So the way I would solve this is I would start back at the beginning where I had it, x equals the cubed root of 125. And I would actually just take the cubed root of 125. This is as simple as just typing this in your calculator. Your phone has this. I mean, it just depends on which phone you have, right? So I've got an iPhone. So this actually has it. The way you work this on your phone, and I'm sure a lot of people already know this, is you just type in 125, and then there's a button for the square root. So you'll see here it says 2 on the outside, and then in square root of x. So that would take the square root of that number. This is a 3 as my index, and then it says root x. So that would take the cubed root of that number. So the cubed root of 125 is 5. There's another way, and maybe you don't know this, I don't know. But another way to do that to any degree is to use this button here. So that says that my index is y root x. So let's check this out and let's make sure I remember how to use this. So if I want to figure out what the third root of x is, or the third root of 125, I can type in 125. I hit that button, that index of y root x, and now I type in the index that I want. So if I want to take the cubed root, I'd hit 3 equals 5. Okay. So for example, the way these really get handy is if I have, I don't know, 2048. Well, 2048. And let's say I want to take the 8th root. I don't know if this is going to work out or not. I'm just making this up. But let's say I want to take the 8th root. So the way I do this is if I want to take, I'm going to write this down. If I want to take the 8th root of 2048, here's how it would work. I'd type in 2048. I'd hit that button that says y root x. I'm assuming Android phones would have the same thing. So I hit that. And now I type in the index that I want, which is 8, the 8th root. So of course it doesn't work out nice because I just made it up. But the 8th root of 2048 is that nastiness. Okay, so that's how you could use that. Some people might have a scientific calculator at home or a graphing calculator. Awesome. We're not going to be able to use those in class, I don't believe, because we can't share materials. So I don't think we'll be able to use the class set. But your Chromebook, your calculator, you can always Google, Desmos has a scientific calculator that you can use and use that as a calculator as well if you don't want to use that. Okay. So that's kind of a long explanation for what we're doing here. So we type this into our calculator, x equals the cubed root of 125, which was 5. So in that case, our answer would be 5. This is just kind of going into a long, definition of that. Let's keep reading here. Consider if there are others. So other real roots is what it's saying. Consider if there are other roots. To determine this, set the expression equal to 0 and factor it. So we started off with, let me get a fresh piece of paper. We started off with x equals the cubed root of 125. We said that I could rewrite this by basically cubing both sides. So on the left, I have x cubed. On the right, like I said, the cubed roots and then the cube just undo each other. So I have 125, okay, which is what they should have here. So what they're saying is to find out if there's other roots, you can set this equal to 0. So I would have to subtract 125 from both sides. So I have x cubed minus 125 equals 0. And then factor it. There's different ways to factor this. You can do guess and check. There's actually a formula to take all this information, our values here, and plug it in. You can use synthetic division or long division. Again, lots of different ways to factor it. I'm not really concerned about factoring a cubic right now, so let's go ahead and just keep going with their example. So they're factoring it, and they got x minus 5 times x squared plus 5x plus 25. And of course, that still equals 0, okay? So if we look at these factors that we got, again, I'm not really concerned about spending time factoring this or plugging into it a formula or anything like that. So don't be concerned about that. I don't think we're gonna run across that. If we factor this cubic, we'll have x minus 5. So that we would set equal to 0 and then solve. So there's my answer from before, the x equals positive 5. This one right here, you can't factor. It is factorable. You could plug that into a quadratic formula and get some really nasty numbers, but it's not nice and neat. You can't use our x method or anything like that, because in this case, a times c is 25, b is 5. There are no two nice numbers that are going to multiply to 25 and add to 5. So we wouldn't be able to factor that. So let's keep looking and seeing what they're saying. Gets the root of 5. The discriminant of the expression is, oh man, I can't remember offhand. We've talked about discriminants. That's just the part of the quadratic formula that's underneath the square root, b squared minus 4ac. So if you remember that part back from factoring, the discriminant, depending on if it's positive or negative, is going to tell you how many roots you have. If it's positive, there's 2 roots. If it's 0, there's 1 root. If it's negative, which in this case, that discriminant is negative, then the roots aren't real. There's no real roots. They're imaginary, which again, I don't want to get too deep into right now. That's more of a pre-calculus thing. But what that discriminant is telling me, because once you plug it in, it gives me a negative value, that there's no other real roots. So therefore, 5 is the only real root of 125. All right, and then they got a part B here. What are all the real 4th roots of 16? So same process as before. X equals the 4th root of 16. You could type that in your calculator. Let's actually do that just to practice it. Okay. So the 4th root of 16. So the way we're going to do this, we don't have a button that says the 4th root. We have this button right here that says y root x. So you type in 16 you hit the y root x button. And then because we want the fourth root, we'll hit 4. And that gives me 2. That gives me part of my answer. So let's go ahead and keep that in mind. Here, what they're saying, instead of just typing in the fourth root of 16, what you can actually do is take that equation, just like we did before. We can raise each side to the fourth power, and we get x to the fourth equals 16. And then you can go through and you can factor that fourth power degree polynomial. What that's going to give me is both positive and negative 2, because remember, when we take the square root of a number, you're always going to have the positive and negative version of that. So for example, if I have x squared equals 4, right? We square root both sides and we get x equals positive and negative 2, because positive 2 times positive 2 is 4. And negative 2 times negative 2 is 4. So you always want to include the positive and negative version. Well, in this case, x to the fourth equals 16. We're taking the fourth root of both sides. The same thing applies. Any even degree, you're always going to take the positive and negative version. It's always going to work out like that. So in this case, we'll deal with positive and negative 2. You could see you have x to the fourth minus 16 equals 0. They just took this equation. Well, let's start off right here. They took the equation. What values of x will be my answer when I take the fourth root of 16? So I raise both sides to the fourth power. I get x to the fourth equals 16. I set the equation equal to 0 and factor, and then I get x equals positive and negative 2. Negative 2 from the first factor, positive 2 from the second factor. Keep in mind this third factor, you cannot factor it. X squared plus 4, those are, again, are imaginary numbers, just like we saw in that first example. So since you can't factor x squared plus 4, you're not worried about it. Just ignore it. You're only concerned with those 2 factors right there. All right. Example 2. Understand rational exponents. What is the meaning of the exponent in the expression 16 to the 1/4? What I want to do is kind of go back and talk about what I said earlier. 16 to the 1/4. If you have a base, it doesn't matter if it's 16, it doesn't matter if it's x, it doesn't matter what the base is. If you have something that's being raised to a fractional exponent, the way you can piece this together is my numerator, the number up top, is going to be my exponent. And then that denominator is going to be my index. Okay, so it's exponent over index. The way I remember this is it's alphabetical. E comes before I, right? A, B, C, D, E. So that's up top. Exponent, E is up top. HI, index is on the bottom. So it's alphabetical. The E comes before the I, so the E is on top, the I is on bottom. So what this is telling me, let's go back to their example, 16 to the 1/4. That's telling me that 1 is the exponent of 16. So it's 16 to the first power. And that 4 is the index. That's what I'm taking the root to, the fourth degree. So I could write 16 to the 1/4. I could write the fourth root of 16 to the first power. Okay, that's the way it works. Let me just make up another example here. X to the 3/4. Okay, remember that top number is my exponent. So it's my base's exponent. The bottom number is my index. So I can rewrite x to the 3/4 as the fourth root of x cubed. The top number is my exponent, so it's the exponent of that radicand. The bottom number is the index, so that's the number that goes on the outside, the root. So let's see if I think that's what they're essentially getting at here. To interpret a rational exponent, so basically an exponent that's a fraction, Look at what happens if you extend the properties of integral exponents to rational exponents. Assume the power of a power property applies to exponents in the form of 1 over n. So they're starting off with 16 to the 1/4. They're kind of going at it a different direction. They're saying that instead of 16, they're going to write 2 to the 4th, because 2 times 2 times 2 times 2 is 16. So instead of 16 to the 1/4, they're saying 2 to the 4th to the 1/4. This is where this power of a power comes into. Notice that we have a base of 2 that's being raised to a power of 4, and then that is being raised to a power of 1/4. Okay, so they're just rewriting that base number as 2 to the 4th. We remember, hopefully, and this is something we'll cover and we'll review, that when you're dealing with this power to a power rule, all you're doing is multiplying those powers together. So if I say 2 to the 4th to the 1/4, all I'll do is multiply 4 times a 4th, which is 1. So 2 to the 1st is the same thing as 2. What I really want to emphasize with this example is it depends on the problem you're dealing with. There's always different ways to represent something. And what they're saying here is that this is the same thing as this, which is the same thing as this, which is the same thing as this. Okay? You can write all of these problems, in this format in any of these different ways. Okay? It just depends on one way, one format might help you solve for a variable versus another. They might give you a question in one format, and then let's say they give you a question in this format, then you have to be able to understand, okay, that's just saying the 4th root of 16. Some questions you'll actually have to take that base and rewrite it. So you get something like this. 4 times 1/4 is 1, so that's easier to do in your head. It just depends. So just be aware of that you can go between different formats. Let's just make sure we're not missing anything. Here they're just saying in general, so instead of talking about specific numbers, I can use an algebraic definition to say that x to the 1/n power is the same thing as n root x. Okay. What is the meaning of the exponent in the expression 27 to the 2/3 power? Well, we've already talked about that. 27 to the 2/3. That's the same thing as, again, 27 is my base. It's exponent over index. So my exponent is 2, my index is 3. So 27 to the 2/3 power is the same thing as the cubed root of 27 squared. They go hand in hand. They're the same thing. So keep that in mind. Again, the way I remember it is exponent over index. E comes before I in the alphabet. So the top number is your exponent, the bottom number is your index. So they're saying that 27 to the 2/3 power is the same thing as 27 to the 1/3 power raised to the 2nd power. Keep in mind, 27 to the 1/3 power squared. These rules, this is called the power to a power rule. What happens when I have something being raised to a power and then being raised to another power, hence the power to a power rule? All I'm doing is taking that base and I'm multiplying those exponents. 1/3 times 2. Okay, so power to a power, the relationship is I'm just multiplying those exponents. 1/3 times 2 is the same thing as 2/3, which is what we started with. So all they're doing is just kind of manipulating what we're starting with and rewriting it different ways. So just be aware of that. So they took what we started with, they just kind of rewrote it in a different way. And then instead of 27 to the 1/3, they're saying the cubed root of 27. The cubed root of 27, you could just take your calculator and type that in. That's going to be 3. So instead of the cubed root of 27 to the 2nd power, they're saying 3 to the 2nd power, which is also 9. I think the reason why they're really emphasizing this is a couple of things. One, which I'm totally in support of. I think it's really important to understand where all of this information is coming from. How is the calculator just randomly taking 27 to the 2/3 power and getting 9, right? Because you could type that in the calculator. You could type in 27 to the 2/3 power. If you go to your Google search button and type that in, it'll give you 9. But this is a way where you can walk yourself through step by step, almost without even writing something down, and be able to piece it together by yourself instead of just a calculator randomly coming up with 9. Okay. So, just like I said before, be comfortable with going from one format of something to the next, right? You'll have to know your properties, right? Like power to a power rule. If you didn't know the power to a power rule, you wouldn't have been able to recognize what happened here. But this is just a way that you can walk through it yourself. We're on the top of page 241. So we're looking at this concept, interpreting fractional exponents, which this is just summarizing what we talked about in the first two examples. The index, so that's what we're taking the degree of the root. The index of a radical is equivalent to the denominator of a fractional exponent. That's what we talked about. X to the 1/4. 1 is the exponent of x. 4 is the index of what I'm talking about. In general, if the nth root of c is a real number, then the nth root of c is the same thing as c to the 1/n. So those, again, that's just showing the relationship between those two things, between radicals and fractional exponents. And then furthermore, you can put these things in lowest terms by just basically going from one form to the next, right? So they're starting off with c to the mnth power. They're breaking up m and n by using the power to a power rule. So instead of m over n, they're saying 1/n times n, m. Then they're rewriting c to the 1nth power as n root c, right? So just like the example we just looked at is what they're talking about here. Example 3 on page 241, evaluate expressions with rational exponents. They're starting off with three different things. So 32 to the 3/5 power, then 27 to the negative 2/3. That's interesting. And then 50 to the 3/4. So let's go ahead and look at these. 32 to the 3/5. Okay. 32 to the 3/5 power. You can see what they're doing is they're starting here, and then they're using they're undoing the power to a power rule. They're taking that power, they're breaking it up as two separate powers, and then they're simplifying it as they go. So they took 3/5, they broke that up as 32 to the 1/5 power to the third power. And then the 1/5 power is basically saying the 5th root of 32. So they took the 5th root of 32, which is 2. They still had the third power on the outside, so 2 cubed is 8. Okay. Keep in mind that I can go to my calculator and just type this in. I can type in 32 to the 3/5 power. It depends on what calculator you have. Let's check and see if you can do it on your phone. I don't know. We'll try it out. Our calculators in class, you can do this too. So 32. And then if I use the index y root x button, and then let's see what happens. If I do 3, no, it's not going to let me. Let me try something else. 32, my y root x button, and then I'll use parentheses. Let's see if it does it. 3/5. No. So either I'm screwing something up or I just can't. I don't know how to do it on the phone. But what you could do is just go into your Google search bar, and type in 32 to the 3/5 power. Make sure you're using parentheses around 3/5. Otherwise, it's going to screw it up, and it should give you 8. But again, like I said earlier, this is just a way that you can make sense based off of properties we've used in the past, like the power to a power rule. You can walk yourself through these problems. Split up that exponent as 1/5 to the third power. Take the 5th root of 32, which is 2, which you can definitely do in your phone. The 5th root of 32 is 2. And then I can just do 2 cubed, which is 8. Okay. The second example, this is that negative exponent one. So this is good. Again, you can just type this in your calculator, but let me explain what's happening here. So instead of 27 to the negative 2/3 power, we broke that up using that power to a power rule. And we said 27 to the 1/3 to the negative 2nd power. Okay. 27 to the 1/3 is the same thing as saying the cubed root of 27. So again, take your calculator, or maybe you're good with this stuff and you can just do it in your head. The cubed root of 27 is basically saying what times itself 3 times is 27. Well, 3, right? 3 times 3 times 3 is 27. So the cubed root of 27 is 3. Now we have that being raised to the negative 2nd power. So I'm going to actually write this down because I want to emphasize something here. What's happening here? Again, you could type this in your calculator and you'll get 1/9. But what's happening is because this exponent is negative, this is what happens. Technically, you have 3 to the negative 2nd power over 1, right? This is my fraction that I have right now. So this negative exponent, specifically the negative, is telling me to take that thing and flip it. Take whatever you have, and whatever's up top is going to flip down to the bottom. Whatever's in the bottom is going to flip up to the top. So let's do that. Instead of 3 to the negative 2nd up top, that's now going to be down below. And instead of 1 down below, that's now going to be up top. So a negative exponent basically tells you to flip that fraction. But one thing I want to make clear is look what happened to that negative. It went away. So once I take that thing and I flip it, the negative sign goes away. I no longer have 3 to the negative 2nd. It's just 3 to the 2nd. So up top is just a 1, 3 squared is 9, and that's how they're coming up with 1/9. So anytime you have a negative exponent, you're going to flip it. Just make sure that negative sign goes away. Once you do that action of flipping it, the negative sign goes away. 50 to the 3/4. Let's see what they're saying. Since 50 does not have a perfect 4th root, so basically you're getting a decimal if you take the 4th root of 50. Let's just verify that. The 4th root is a decimal. So since 50 does not have a perfect 4th root, use a calculator to approximate it, which we just did. So you're not going to be able to kind of walk yourself through that step by step because it's going to end up in a decimal. So they're just saying anytime you have a situation like that, just use a calculator. The go-to, if nothing tells you how far to round it, is 3 decimal places. That's just a common go-to. So if you're doing a problem and they're not telling you to round it, don't write the whole thing. Just round it to 3 decimal places. So in this case, my answer would be 2.659. I think I'm not sure what I pressed. Oh, I pressed 50 to the 1/4. So 50 to the 3/4 power. Let's go ahead and write this out. So 50 to the 3/4. That's the same thing as 3. The top number is my exponent. And then that bottom number is my index. So 50 cubed, 50 times 50 times 50 is that 125,000. Now I will take the 4th root of that. So the 4th root, 18.803. So sorry, I started off with 50 to the 1/4. I didn't catch that it was 3/4. So, and they got 18.80. So example 3b, the Fujita scale rating F of a tornado is represented by that nastiness, where W is the estimated wind speed. So wherever you see a W in here, that's where you're going to input the wind speed of the tornado in miles per hour. What is the Fujita scale rating of a tornado with estimated wind speeds of 100 miles per hour? So essentially, you're taking that formula and just inputting 100 where you see W and then calculating it. So let's go ahead and do that. So this is 3b. F equals the cubed root of, again, we're replacing W with 100. So I'm going to go ahead and write that. 14.1. And I think that entire thing is being squared minus 2. Okay. So this is what I've got. I just inputted, instead of W, I inputted 100, and now is where we solve this. Keep in mind, if I have a fraction being squared, that's the same thing as this. 100 over 14.1 squared is the same thing as 100 squared over 14.1 squared. Sometimes that's helpful, sometimes it's not. It just depends on what you're doing, right? Just be aware of that property. Or I can go from the top and the bottom being squared back to the single fraction being squared. So if I start working this out, 100 divided by 4.1, I'm just using my calculator. 100 divided by 14.1 is a nasty decimal. All I'm going to do is square that. So that decimal squared is this nasty decimal. So what I have now is F equals the cubed root of, I'll keep 3 decimal places just in case, 50.299, and then minus 2. So now I will take the cubed root of that number. So I've already got that number in my calculator. So I'll hit the cubed root of it, which is, I'm going to call it 3.691. 3.691. And then 3.691 minus 2 is 1.691. And I really should use these approximate, right? These approximations. Anytime you're rounding things, you should identify it as approximate. Okay. And that's just a little wiggly equation sign. So let's make sure we got the same answer. Same thing. Let's just see what they did. It looks like they took that original equation, and then instead of keeping the cube root, they rewrote it as a fractional exponent. They simplified what's inside the parentheses, and then either they took the cube root, a 7.09 squared. I'm not sure how they got from this step to this step, but in the end, it doesn't really matter what route you take. We got the same exact answer. F is approximately 1.691. So a tornado with estimated wind speeds of 100 miles per hour is classified as F1 according to the Fujita scale. It's interesting. I didn't even know about that. Fujita scale. Example 4. Got a few more to go. So example 4, simplify the nth roots, simplify each expression. I talked earlier at the beginning that you're not always taking the root of a number. You could have variables as well. Just kind of depends on, a lot of times you'll have both. So just keep that in mind. So what this is saying is the 5th root of 32m to the 15th. You're going to handle numbers and variables differently. So typically what I do is I think about like numbers as step 1 and then variables as step 2. Okay. So what I'm going to think about first is the 5th root of 32, and then I'll take care of the 5th root of m to the 15th. Okay. They are breaking this up and they're rewriting 32 as 2 to the 5th to just emphasize that the 5th root of 2 to the 5th is just 2. I might do it a little bit differently. So let's take a look at it. 4a. 5th root of 32 m to the 15th. Yes. Okay. Like I said, there's a lot of things I can do here. I'm going to think about this as the 5th root of 32. And then I'll take care of that. And then I'll also think about this as the 5th root of m to the 15th. Okay, so just kind of two different steps. Obviously, I could take my calculator and do the 5th root of 32. What they decided to do was, instead of the 5th root of 32, they wanted to rewrite that as 2 to the 5th. Because, right, 2 times 2 times 2 times 2 times 2, that's 32. So those two things are the same thing. My radicand is the same thing. What this is essentially saying here, I can rewrite this as 2 to the 5 over 5, right? Exponent over index, exponent over index. Well, 5 divided by 5 is just 1. So really what I have here is a 2. So this step of just rewriting this as 2 to the 5th is just to emphasize that these two exponents and indexes are the same and they simplify down to 1. If you want to just type this in your calculator, you can. It's the same thing. This is a little bit different though. We are not breaking this up as, the same exact thing as we did with numbers. So they kind of behave a little bit differently. So when you're looking at this problem, they went ahead and broke that 15 up as a power to a power rule. So instead of m to the 15th, they said m cubed to the 5th power. Because remember, when you have a power to a power, all you have to do is multiply those to get that value of 15. So to go backwards, you could just divide it by something. So I could take 15 and separate that as 3 to the 5th power, or 5 to the 3rd power. It just depends on what numbers you're looking for. Now that they had the 5th root of something to the 5th power, they could just eliminate those two things and you're left with just that radicand as your final answer. With this example, though, let me also walk you through another way you can think about this. Essentially, what you're doing is taking m and you're raising it to the exponent over index. 15 divided by 5 is 3. So it's going to be m cubed. You're just essentially dividing those two numbers. Just make sure your exponent is on top and your index is at the bottom. So this problem, the 5th root of 32m to the 15th, simplifies down to 2m cubed. B, the 4th root of x to the 20th y to the 8th. Root. Just remember what we talked about, the relationship between the index and what's happening with your radicand is you're just dividing those two things. So I can rewrite this as x, that exponent is 20, exponent over index, and then I've got y, exponent over index, and then simplify it. 20 divided by 4 is 5, 8 divided by 4 is 2. So the 4th root of x to the 20th y to the 8th is x to the 5th y squared. One thing they're doing here is, because this number is being squared, they're basically taking, let me back up a little bit. If you take a look up here, this is to the 5th root, right? The 5th power. We're taking the 5th root. That's an odd number. This problem down here is the 4th root. 4 is an even number. Kind of like we talked about a little bit ago. If I take, I don't know, the cubed root of 8, okay, my answer is just 2. Because when I multiply 2 times itself 3 times, I get 8. But if I take the 4th root of 16, we're going to get both positive and negative 2. Because 2 times 2 times 2 times 2 is 16. Negative 2 times negative 2 times negative 2 times negative 2 is 16. So when you take an odd degree root, you're just going to have, the positive version. But if you take an even degree root, you have to include the positive and negative. okay? And that's where they're getting with this absolute value sign here. So you'll notice when they had the fourth root of x to the fifth y squared to the fourth power, the fourth root and the fourth power just kind of undo each other. But because it's the fourth root, because the root is to an even power, they have to take the absolute value of that function. Okay, so it's a little bit kind of wonky looking. The absolute value of y squared is just y squared because, again, it's an even power. But because x to the fifth, 5 is an odd degree, you had to leave that inside absolute value signs. So technically, the fourth root of x squared y to the eighth is the absolute value of x to the fifth times y squared. And for this, the exact same reason we just talked about here. Any odd degree, you're just going to take the positive version. There's no way that you can plug in a -2 and get +8. It just doesn't work. But any even degree root, you're going to have to include the positive and the negative version. Okay, so that's why we're not taking the absolute value of y squared, because we want both the positive and the negatives. Good question. Example 5, we're at the bottom of page 242. So use the nth root to solve this equation. I'm going to go ahead and write this out. 2x to the fifth. So just like we do any other equation, your goal here is to try to get x by itself. That's what you're working towards. What I would start with, I can't do anything with this x to the fifth right now because I'm multiplying it by 2. So my first step would be to divide both sides by 2, which gives me x to the fifth equals 32. And at this point, like I said earlier, x to the fifth and the fifth root of x, those things are opposites of each other. They undo each other. So if I have x to the fifth, what I can do is I can take the fifth root, and then those two things will undo each other, and I'm left with just x. But keep in mind, if I take the fifth root of the left side, I have to take the fifth root of the right side. So fifth root of 32, 32 to the 1/5 power, it doesn't matter how you think about it. Again, I would just type it in my calculator. I believe that was 2. So because this is an odd degree root, right? It's an odd degree root. Are you worried about positives or negatives? You're not. Just like we said in that last example, anytime you're cubing something, it's just going to be the positive version of that. It's only when you're square rooting, fourth rooting, sixth rooting, anytime you're taking the root of an even power, that's when you're worried about the positives and the negatives. So for number 5, that would be my final answer. They got a concept over here. Solving an equation in the form of x to the nth power equals c. To solve an equation, so again, this is basically summarizing what we've talked about. To solve an equation in the form of x to the nth equals c, find the nth root of both sides by raising each expression to the 1/n power. So you're raising each expression to the reciprocal of whatever power you're dealing with. So for example, x to the 7th equals, I don't know, 12, just making something up. If n, right, n is 7, what I'm doing is I'm raising both sides of this to the 1/7 power. That's supposed to be a 7. So the 1/7 and the 7 will undo each other. And then on the right, 12 to the 1/7 power is whatever. You could also think about it like this: x cubed equals 12. Raising it to the reciprocal, if that's 7, that's 1/7. If this is 2/3, right, the reciprocal would be 3/2. So it's just that fraction flipped. But if I have something like this, x cubed equals 12, raising both sides to the 1/3 or just taking the cubed root of both sides is the exact same thing. So don't feel like you have to sit there and write out fractional exponents. You could just take the cubed root of both sides and you get the same exact answer. Example 6. Ooh, this looks like a doozy. One cube-shaped container has an edge length. So since it's a cube, that means all the edges have a length of 2 centimeters longer than the edge of the length of the second cube. Okay, so what this is trying to say is all of these edge lengths of this smaller cube here is x. X high, X wide, X long, all that stuff. So this bigger cube up top has an edge length 2 centimeters longer. So this base is X plus 2, the height is X plus 2, the length is X plus 2, right? So this is X plus 2 cubed, basically. The volume of the larger cube is 729, and they're telling you that in the picture. When the larger cube empties into the smaller cube, how much water will spill out? So obviously, if this cube is larger, this is smaller, you're going to have some overflow happening here. So like we said, if we want to solve for x, because that's the reference they're giving us, this is x by x by x. This is x plus 2 by x plus 2 by x plus 2. So what we can do is we know the volume of that first cube there. So the volume of that top cube, it's going to be x plus 2 because it's 2 centimeters longer. And that's going to be cubed equals 729. So what I want to do is solve for x, and then I can figure out whatever they're asking me to do. So in this case, I am going to take the cubed roots of each side. Remember, the cubed root and the cube just undo each other. So I'm left with x plus 2. The cubed root of 729, that's a great question, is 9. So the cubed root is 9. And now I just solve this. I subtract 2 from both sides, so I get x equals 7. Let's make sure we got the same answer. Perfect. X equals 7. So what that's telling me is this cube down here is x, right? X by x by x. So it's 7 by 7 by 7. So 7 cubed, I'm going to go ahead and type that in my calculator, is 343. So this top container has a volume of 729. The bottom container, since it's 7 by 7 by 7, has a volume of 343. And that's what they're saying down here. So they're wanting to know how much is going to spill out. So 729 minus 343 is going to be 386. So that's the volume of water that will spill out because the top cube is larger than the bottom cube. And then we are to our concept summary. So this is basically summarizing everything we talked about. Let's just go through here real quick. This is talking about the index of a radical is equivalent to the denominator of a fractional exponent. So remember, the cubed root of x is the same thing as x to the 1/3 power. Okay. The exponent of the radicand is equivalent to the numerator. So for example, the cubed root of x squared, I'm going to go ahead and write this down. The cubed root of x squared is the same thing as x to the exponent over index. Exponent over index. So the index is the denominator. The exponent is the numerator. That's all that's saying. To solve an equation in the form of x to the n equals c, find the nth root of both sides of the equation by raising each expression to the 1/n power. Again, what that's saying is x to the 3rd power equals 7. The reciprocal of 3 is 1/3. So I'm going to raise both sides to the 1/3 power. Or, to me, it just makes more sense to do this. Take the cubed root of both sides. Just be familiar with different ways you could represent that. It's the same thing, just a different look. So here's some examples and some algebraic definitions. These can get a little bit wordy and a little bit confusing. So to me, looking at examples kind of helps me understand that stuff a little bit better. This is already getting pretty long, so I think I'm going to break this up, and then we will take a look at the next page, which is the practice problems, examples 25 through 43 in part 2.